When a user watches a video on a major platform, their viewing session is tracked on a timeline. Usually, the playhead moves continuously from left to right, but often a user misses a detail, stops, and snaps backward to rewatch a segment. Let's attach some timecodes to that behavior. Imagine a viewer watches from minute 1 to minute 4, then scrubs back and watches from minute 3 through to minute 6. A naive analytics system will log the first segment as 3 minutes of watch time, and the second segment as another 3 minutes. It adds them together and tells the server the user watched for 6 minutes total. This animated diagram shows the mathematical reality. We have 2 viewing blocks, 1 to 4 and 3 to 6. When we map them onto a single number line, the overlap between minute 3 and 4 means the viewer consumed only 5 unique minutes of content. Multiply that 1-minute discrepancy by millions of active users, and the platform's entire dashboard breaks down. Engagement metrics inflate artificially, servers miscalculate the required bandwidth, and advertisers pay for phantom views that never actually happened. Raw temporal data is inherently chaotic. User sessions constantly overlap and fragment. Cleaning up this timeline requires a specific algorithmic approach designed to consolidate overlapping ranges. The initial instinct for developers is to build a system that takes every single user session and compares it against every other recorded session to check for an overlap. This diagram visualizes that brute force approach. Evaluating every block against every other block scales exponentially. It creates an O of n squared of time complexity that overwhelms processing power and quickly grinds the servers to a halt. To fix this, we implement the first phase of the merge intervals algorithm. Before doing any comparisons, the system intercepts the data and sorts every interval purely by its starting time. By arranging the data this way, any 2 viewing sessions that could possibly overlap are forced to sit directly adjacent to one another in the list. Sorting shifts the entire perspective of the problem, eliminating the need to search the entire database. We reduce the operation to checking immediate neighbors. This brings us to phase 2, the linear sweep. As we see in this diagram, the system locks on to the first recorded block on the staircase and designates it as our current active interval. Then it looks at the start time of the block right below. The algorithm makes one simple logical check, dropping a boundary line from the end of the current block. It asks, does the next block begin before this cutoff point? If the answer is yes, we enter an absorb state. The system extends the active block's ending boundary to cover the new data and fuses the two together into a single continuous timeline. But there is a logical trap here involving nested sessions. Imagine a user streams a 5-minute video, then watches a 1-minute clip in a second tab that starts and stops entirely within that original window. To handle this, the algorithm runs a max function on the ending boundaries. It compares the end of the current block with the nested block, keeping whichever value is higher, cleanly swallowing the smaller session without inflating total time. Eventually, the sweep finds a block starting completely after our active interval ends. This triggers a sever state. The system locks the current block, saves it to the final array, and moves the highlight box to track this new segment. By continuously expanding boundaries and saving completed intervals, the system can process an infinitely long timeline of overlapping data in a single, uninterrupted forward pass. Looking at this C++ implementation, the heavy lifting happens immediately. Before entering the main loop, we call the language's built-in sort function to align all the start times. From there, the traversal logic iterates through the vector. Instead of keeping a separate variable for the active interval, the code constantly references the last element inserted into our result array by using the back command, comparing its end time against the incoming data. A common software engineering trap here involves intervals that touch exactly, like 1 to 3 and 3 to 5. If a developer uses a strict less than sign to check for overlaps instead of a less than or equal to sign, these adjacent blocks will incorrectly fail to merge. The code snippet itself is remarkably short, but its structural integrity relies completely on the mathematical precision of that single inequality. The efficiency of this pattern comes down to the initial sort. While the linear sweep executes in O of n time, the sorting phase dictates the overall performance, giving us an optimal time complexity of O of n log n. The memory constraints are equally tight. The operation requires just O of 1 auxiliary space if sorted in place, or O of n if we need to allocate memory to store the newly consolidated result array. Back on our platform dashboard, this generated data visualization shows the algorithm acting as a filter. Chaotic, overlapping sessions are caught, evaluated, and rapidly consolidated into a stable, accurate metric line. This logic scales well beyond streaming video. Network engineers use this exact pattern to resolve bandwidth conflicts on active transmission channels, while enterprise systems use it to optimize employee shift scheduling across thousands of retail locations. Merge intervals serves as an architectural defense against temporal data corruption, turning a chaotic timeline into clean, actionable intelligence.